Hello dear student, welcome to the next lecture in molecular spectra. Today we will be dealing with electronic spectra. In this video, we will be talking about electronic spectra, the salient features of molecular electronic spectra, the sequences and progressions that we see in the electronic spectra, and also about the Franck-Condon principle. Electronic spectra arises due to rearrangement of electrons within the electronic shells. We know that the atom has a nucleus and the electrons revolving around them are arranged in shell from the Morse model. Therefore, when an electron interacts with a light, it will absorb energy from that radiation and goes to a higher level. In the higher level, it is unstable, therefore it will release energy and come back to its normal state. And this is what gives us spectra. So, when we irradiate any sample with a radiation which is powerful enough to make electronic transitions, then the resultant will give us the electronic spectra. This electronic spectra can be absorption spectra or emission spectra as per our requirements. And this electronic spectra arises due to change in the arrangement of the molecular electrons. Similarly, in the case of molecules, also molecular electrons are rearranged when they are irradiated with an energy which is equal to the energy between the electronic states. And since this is the case of electronic transition, the energy should be high enough to make electronic transitions. So the energies involved here are large. We already know that the electronic spectra didn't arise as its own, because the electronic levels are comprised of vibrational levels and rotational levels. Electronic spectra also comprises of the vibrational coarse structure and the rotational fine structure. Now let us see the salient features of electronic spectra. We know that the electronic spectra arises due to transition of electrons between two electronic levels. If I denote the lower electronic level by double dash and the higher upper electronic level by one dash, then we can see that the single electronic level will be consisting of different vibrational levels. And we have seen in this in our previous video, a single electronic level will be comprised of different vibrational levels, and a single vibrational energy level will be comprised of different rotational energy levels. Therefore, transition from one electronic level to another electronic level implies that the transition doesn't happen from one single energy level to another single energy level. The transition actually happens from a multiple rotational vibrational energy states to another multiple rotational vibrational energy states. Therefore, the resultant spectra we get is not a single line but a combination of different lines we expect. And since these electronic transitions have to be between the electronic levels, they actually are lies in a very good energy range, so they are visible and we can see these electronic transitions. And what we see when we light up a fire, or what we see in a spectrum in our lab, everything is electronic transitions, because electronic transitions is the only transition we can see with our naked eyes, because they fall in the visible UV region. All other vibrational or rotational transitions falls in the lower frequency region such as IR or microwave, and for that we need highly sophisticated devices to look into. So all the spectroscopy devices or the lab experiments we do are actually falling into the electronic spectra prism. So since the electronic transition, some electronic transition will give rise to a lot of vibrational energy change. A little electronic energy change will result in a lot of vibrational energy change, and a single vibrational energy change will result in a heavy rotational energy change. Therefore, in a single electronic transition, we expect the vibrational and rotational energies also to be involved. And the rotational transitions falls in the IR region, which gives the cos structure, and the the vibrational gives the cos structure and it falls in the IR region, and the rotational transition gives the fine structure and it falls in the microwave region. And these electronic transitions can be studied with both absorption and emission spectrum. All molecules, including the homonuclear molecules, exhibit electronic spectra. While we were studying the vibrational and rotational spectra, we have seen that the homonuclear molecules such as oxygen, nitrogen, hydrogen, etc. doesn't give us spectra because they doesn't have a permanent dipole moment. But in case of electronic spectra, since the rearrangement of the electronic charge or the redistribution of the electrons within the shells give rise to an instantaneous dipole moment change, even without a permanent dipole, these homonuclear molecules such as oxygen, nitrogen, hydrogen gives us the electronic spectra. So all molecules are capable of giving the electronic spectra irrespective of whether they have a permanent dipole moment or not. Since we have seen that one electronic transition is accompanied by a vibrational and rotational transitions, we can see that the energy of the molecule is a combination of its electronic energy, its vibrational energy, and its rotational energy. We have seen that the electronic energy will be the energy of its electronic state or the shell. The vibrational energy level or the vibrational energy can be found using this formula, and we have seen this in our previous classes. And the rotation here nu zero is a frequency with which the molecule vibrates, and the rotational energy is given by Bj into J plus 1, where J is the quantum number for rotation. Here in this picture you can see that the single atom, if it was in the case of a single atom, the electronic transition will happen from one single level to another single level. If it was in the case of an atom, we can see that one single atom the transition will happen between just two energy levels, and this will give you a single line. But in the case of a molecule, this single energy level is composed of different vibrational energy levels, and the transition between these vibrational energy levels also happens. Therefore, instead of getting a single level here, we get multiple transitions are possible. So all these spikes in the second figure here indicates the different transitions which is happening between the vibrational energy levels. If the molecule is large enough, all these vibrational energy levels will be packed together, and this will gives us the vibrational cos structure. The transition frequency shows the bands in the electronic transition in the vibrational cos structure and also the rotational cos structure. So instead of getting a single line in the spectra, what we are expecting is multiple lines, maybe discrete or maybe continuous if these levels are more and more closely arranged. So the transition frequency, or the frequency which we observe in the spectra, will have the energy lines which will be the combination of electronic energy lines. This will have the electronic energy lines. It can have the transition between the frequency transition between the vibrational energy state. Here dash is given to the higher energy state and double dash denotes the lower energy state. Therefore, and we can see that the transition frequency will be a combination of difference between the electronic levels, difference between the vibrational levels, and difference between the rotational levels. Difference between the electronic levels will be the energy of the shells. Difference between the vibrational energy levels will be given as V dash plus half into nu 0 dash. This is the frequency with which the molecule vibrate when it is in the excited state, and nu 0 double dash is the frequency with which the molecule vibrates when it is in the ground state. So the frequency of vibration is different when it is in the ground state and it is in the excited state. This is most probable because when it is in the excited state, it has a higher energy, so it execute higher vibrations. Therefore, the frequency of vibration will be different when it is in an excited state. Similarly, in the case of the rotation, we can see that it is a rotational energy of the excited state minus rotational energy of the ground state will give you the frequency transition. Therefore, the single line or the multiple line which we observe will be a combination of these three frequencies. In the electronic spectra, and this is all the kind of transitions which will happen, and given in the picture is the kind of transitions which we will see in electronic spectra. So in an electronic spectra, we expect sequences and progressions. So what is a sequence and what is a progression? A single electronic transition doesn't give you one single line in the spectra but give you a band system. As we have already seen, since it is involved with the vibrational and rotational transitions, it will give you a band system. We are now looking only into the vibrational cause structure. We are not going deep into the rotational cause structure for this lecture. Therefore, we will be sticking on to the electronic transition and the vibrational sublevels which are involved in it. So, what are progressions? Progressions involve set of transitions with a common upper level or a common lower level. Given in the picture, the first three transitions here gives you the progressions, and these are shown as the progressions. And progressions are transitions in which we have a fixed level. Either the level is the lower level is fixed or the upper level is fixed. And if the lower level is fixed, the upper level changes. And if the upper level is fixed, the lower level changes. So this gives rise to two different progressions. As you see, it progresses in levels. So it is called progressions. If based on whether the upper level or the lower level is fixed, we have two types of progressions. That is V double dash progression and V dash progression. If V double dash is denoted by for the lower level. Double dash is what we use for the lower level. So if the lower level is what progresses, that is, if the upper level is fixed and the lower level is what progresses, then this is known as a V double dash progression. In this figure, this third transition step shown is the V double dash progression. In V double dash progression, V dash is fixed, and that is the upper level is fixed, and V double dash, that is the lower level, is progressing. Therefore, it is known as a V double dash progression. Example for this is 0 0 progression, 0 1 progression, 0 2 progression. Here you can see that this level is 2 and this level is 0 1 2 3 etc. So the progressions here is 2 0 progression, 2 1 progression, 2 2. All these transitions come under the V double dash progression. Similarly, if the V double dash is fixed but the V dash is what? Progressing, and that is in the first two cases. If V dash is progressing, then it is known as a V dash progression. So for a V dash progression, what we have is the lower level is fixed and the upper level is progressing. For example, it is 0 0 1 0 progression. You can see that this is 0 0 progression, 0 0 transition. This is 1 0 transition. This is 2 0. This line is 3 0. This line is 4 0 and 5 0. Similarly, this is how we progress. So for one level is fixed while the other is progressing, and this is known as progressions. Similarly, there is another set of band system arises, and that is known as sequences. Sequences are a group of transitions in which the delta V is to be same. That is, here the difference between the levels 0 0 transitions, then there is no difference. The delta V is 0. If it is 0 1 transition, the delta V is 1. 0 2 delta V is 2. 0 3 delta V is 3, and so on. So in case of progressions, the delta V always changes. But if we have a set of transition in which the delta V is constant, then those set of band system are known as sequences. Here, in these last two transitions given here are sequences. For the first band system, the delta V is 0. That is, transition is made from 0 0, 1 1, 2 2, 3 3, 4 4 and 5 5. Here the upper vibrational state and the lower vibrational state are the same. Therefore delta V is 0. And if delta V is equal to 1, then the bands here are 0 1, 1 2, 2 3 etc. If a delta V is equal to 2, the bands we expect is 0 2, 1 3, 2 4 etc. And these transition will give us sequences. So what is the difference between progression and sequences? For progression, either the upper level or the lower level is fixed and the other level, the alternate level, will be progressing. While in the case of sequences, the delta V or the difference between the upper level and the lower vibrational level is said to be same, and these gives us different band structures. Before we move on to the next topic, I want you to introduce to a concept, that is potential energy curve. You might have seen in your quantum mechanics and in your classical mechanics courses that some potential energy curves looks like as we seen in the picture. So this is a typical potential energy curve. You can see this in any bound system. Here the bound system we are considering is a molecule. Here the hydrogen molecule is taken as an example. Hydrogen molecule is a bound system. So this curve, this particular potential energy curve, this curve is plotted with potential energy against the internuclear distance r. Okay. So this curve, this particular curve is called a Morse curve. Let us see what are the features of a Morse curve. A Morse curve have three extremum points. One extremum point is here, one is here, and one is here. You know in mathematics what is the extremum points. Extremum points is where the curve is, or the change in the curve is maximum, or the change is 0, is what we have in the extremum points. So the extremum points, when it reaches the 0 here, here and here, we have three extremum points in this particular curve. This extremum point with the minimum energy is known as the minimum of the curve. This is the minimum of the curve, and these 2 points we have maxima. So here we have the minima, and 2 points we have maxima. This maxima points are called the turning points. Turning points. So we have 2 maxima and they are called the turning point, and we have 1 minima, and that is known as the minimum position. Do you remember this simple harmonic oscillator? For simple harmonic oscillator, you have 1 minimum energy position, the position of equilibrium, and it can oscillate, and it will come to this position and go back. It will go to this position and come back. In this system, these 2 points, the extremum points, are the turning points. So these are the turning points in this particular system. This is a very simple system, but in when we are coming to atoms and molecules, we consider something known as an unharmonic oscillator. So something which is a little more complicated than the simple harmonic oscillation or the simple pendulum, but the potential energy curve will give you 2 turning points and 1 minimum point. So the hydrogen molecule, since a hydrogen molecule is 2 mass separated with a distance system, we can consider it as an oscillator. So the oscillator potential is shown here. We can have the minimum when the hydrogen molecules are at the minimum position, and we have 2 turning points. So this difference between the minimum and the 0 point is known as the bond energy. So this is the bond energy, and the distance from the 0 point to the minimum is known as the bond length. The mean bond length is given by the 0th position and the distance between the minimum. And this minimum length here is denoted by Re. So this is the nuclear distance, or the mean nuclear distance, or the bond length, and is denoted by Re, and here we have the potential energy. Since we are talking about transitions, we have the ground energy state and an excited energy state. Every energy state is denoted by a similar curve. So if the atoms get excited, it changes this potential curve, as well as it changes the shape of the potential curve, as well as its minimum distance or the internuclear distance. So here shown is a ground energy state. This is the potential curve of the ground energy state. In this potential curve, this is Re. So Re is this point, and we can see that this is the dissociation point. Here dissociation point means a point above which the atom is no more bound. This is the region where the atom is bound. So any potential energy above than this, the atom is not bound to each other. Then they are no more molecule. They have dissociated. So here we have one electronic state is what is denoted by this potential energy curve. So inside one electronic state we have different vibrational states, and inside one vibrational state we have different rotational energy state. Here the ground state is given by Re. Let me put a double dash so that you can identify it as a ground state, and you can see that the minimum of the excited state Re dash falls at a different level. Here we have the separation. That means that the separation between the atoms has increased since when they are in an excited state. So when the atoms get excited, the potential energy curve changes in its shape and also changes in its position in terms of the internuclear separation. Now let us step into the Franck-Condon principle. Here see we have two potential energy curves, and this denotes the ground state and this denotes the excited state. So the Franck-Condon principle is used to explain the intensity distribution of lines in vibrational electronic spectra. That is, in electronic spectra, instead of having a single line, we have a band of lines which arises due to transitions between the vibrational state also. And these bands which arises is not always a single intensity band. Some bands or some transitions are more probable, or they are more intense than the other bands, other nearby bands. Say 0-0 transition have a higher intensity than 0-1 transition, which means that the 0-0 transition is highly probable. It is highly likely to happen than the 0-1 transition. So the Franck-Condon principle actually tells us why some transitions, say 0-0 or 0-1, is highly probable or likely to happen than the other set of transitions. And this principle, which is plotted by Franck, is known as a Franck-Condon principle. So according to Franck-Condon principle, an electronic transition takes place so rapidly that the molecule's internuclear distance does not change appreciably during transition. We know that a molecule can be considered as an oscillator, and it oscillates between its mean position. So it has an oscillating frequency. If the transition from the ground state to an upper electronic state happens so rapidly than the frequency of this oscillation, this molecule's length, the interatomic length, will remain almost the same during these transitions. So the Franck-Condon principle tells us that these electronic transitions are very rapid, so that the molecule's internuclear distance, or the vibration between the molecules, does not change appreciably during the transitions. If it means it does not change appreciably, that means the bond length R is same. We know that in this plot we plot potential energy against the bond length, right? Here we plot potential energy against the bond length R, which means that the bond length R have to be same for the ground state as well as the higher state. So if for the ground state, if this is the Re, then it have to be the same for the Re dash case also. The bond length have to be same. I am not talking about minima. The bond length R have to be same for the lower energy state, the ground state and the excited state. So if these are same, which means that all this have to fall in a single line. So the transition here occurs in a straight line. So they are represented by vertical lines because the internuclear distance, the R, is same. And also the transition occurs between the extremum or the stationary points. As we have discussed, it has 3 stationary points. It has a minimum and 2 turning points. It has 3 stationary points and the transition happens between the stationary points. And the nucleus is stationary at its turning points and minimum. And this is how we explain the Franck-Condon principle using classical theory. So using classical theory, how we explain is that the transition occurs between the stationary points, and the stationary points here are turning points and the minimum. So the line which straight from the minimum of the ground state connect to the stationary point of which state. Say if this state is 4 and this is 0, then in this case the 0-4 transition is the highly probable or the highly intense line, and all other transitions, say which is not connected with a straight line, are less probable. We can use quantum theory also to explain the Franck-Condon principle. In your elementary quantum mechanics courses, you might have seen this psi square, mod psi square, which is called the probability density. So probability density actually tells us how probable are we to see that atom in that particular state. Right? How probable is that the electron or the atom or the system is in that particular state. And this probability density falls along the middle in the ground state. You might have seen these diagram also. It falls almost in the middle in the ground state. But as we goes towards the higher state, the probability density shift towards its extremum points, and this is what we have seen in quantum mechanics. So the transition in the ground state which happens from the highly probable position, the transitions take place from the highly probable position, that is from the center of the ground state to a highly probable position which is vertically above. So the highly probable position which is vertically above is any level's extremum point, and the level and the extremum point which come in close is here, which is at the 2. So in this case the 2-0 transition is the highly probable transition. So what does this quantum theory says us? It is based on the probability density. Probability of the system to when it is in the ground state, V is equal to 0, then it is in the middle, and as we go to the higher state, the probability shifted towards the extremum position. So it comes to an extremum point which is vertically above the ground position. This vertically above because this R of or the internuclear distance is same for the ground state as well as the excited state. So it goes for some point which is vertically above and also resembles the ground state. So the transition occurs between the vibrational energy levels which resembles each other. You can see that this particular region resembles this particular region. So the transition occurs between vibrational energy levels which resembles each other, and the transition should be here also represented by vertical lines since the internuclear distance is kept same during the transition, and the probability density is maximum at the center for the ground state when V is equal to 0, and the probability density is maximum at the extremities when at the excited state. So it goes from the highly probable state to another highly probable state, which happens to fall in the turning points or the extremum position. And using quantum theory also, this is how we can explain the Franck-Condon principle. So according to Franck-Condon principle, the most intense line or the most probable transition is where the vertical line meets. So vertical line from the ground state here meets the point here, and this is where we get it. The fourth line here as a vertical line means we have a sample distortion here in this picture. So this is how we get the vertical lines, and suppose in this picture here the transition occurs between 0 and 3. The third line is where the vertical line meets. Then the 0, 3 position will be the highly intense position or the highly intense line, the most probable transition, and all other transitions 0, 2, 0, 1, 0, 0 as well as to the higher 0, 4, 0, 5, 0, 6, all those progression will come in the lower position or lower intensity. So this is how we get the spectra. So depending upon the position of the minimum, that is Re dash and Re double dash, we can see different type of spectrum. When Re dash is equal to Re double dash, which means that the minimum of both the excited state as well as the ground state falls into the same R. Here R with respect to energy is plotted. So this Re dash, this energy state, excited state is not shifted. It is exactly above the ground state. In such cases, the most probable transition is the 0, 0 transition itself. In that case, we will get a high intense line for 0, 0 transition and a lesser intense line for all other progressions such as 0, 2, 0, 1, 0, 3, etc. And this is the case of oxygen molecule. When we get the spectrum of oxygen molecule, we have a maximum at 0, 0 and all other lines are subsequently of higher lower intensity. Another case is when the Re dash, that is the excited state energy or the bond length is higher than the minimum of the ground state, that is Re double dash. So when Re dash and Re double dash is separated, and if Re dash is higher, or maybe if the Re dash it shifted towards this end also. Similarly in both the cases, here the delta V is not equal to 0 and the maximum probable will be where the vertical line is going to meet. Here the vertical line is meeting at 2. So here the 2, 0 transition is the highly probable one. Here the 2, 0 transition is a highly probable one, and all other transitions such as 3, 0, 1, 0, 0, 0, etc. All these transitions falls in the lower probable or are less intensity. And this is the case of carbon dioxide molecule. And another case is that if the Re dash, that is the internuclear distance of the excited state, falls in the dissociation region, or that is the molecule is have a very high bond length or has dissociated, then in such a case this Re dash and Re double dash distance between them will be very large, and the minimum occurs and the maximum line which we get will be in the continuum, that is this part, or the maximum occurs will be in the continuum region. That is the vibrational state here of the excited state to which the electron goes actually is in the dissociation limit. So what we observe is a continuum towards so this transition which will be somewhere in the continuum, but we can't just distinctly see which level is it, because all the levels are closely packed when the level is in and around the dissociation. All the levels are closely packed. So what we see here is a very blur image of continuous levels. So this level may be somewhere inside the continuum, and this is the case of the iodine molecule. And this is the Franck-Condon principle. So what was the Franck-Condon principle? According to which the molecules, the internuclear distance of the molecules will be the same during electronic transitions. So all these electronic transitions can be represented by a straight line. If the transition happened from a ground state V is equal to 0 to some other excited state V is equal to 1, 2, etc., then where the vertical line meets, and that particular transition will be the most probable transition, and that line will be most intense, and all other transition will have a less intensity. So in this lecture we have learnt about electronic spectra. We have seen that the electronic spectra arises due to rearrangement of electronic charge or electrons between the shells or the electronic levels, and this is accompanied by the distribution in the vibrational energy levels as well as the rotational energy levels. We have seen that it falls in the visible region, and also all the molecules gives us the electronic spectra. Even the homonuclear molecule gives us the electronic spectra. We have seen the salient features of the electronic spectra. We have seen band structures, that is sequences and progressions. For progression, either the lower energy state or the higher energy state is fixed and the other lines are progressing. For sequences, the delta V is fixed. We have seen the Franck-Condon principle, which is used to explain why some lines are more intense than the others, and using Franck-Condon principle we have seen that the internuclear distance, intermolecular distance remains the same in case of electronic transitions. So the transitions can be represented by vertical line, and this vertical line represents the highly probable transition. So by this we come to end of this lecture. Thank you.